One important situation you're supposed to understand is what is actually happening when we do the electrolysis of water. So this is the case where we're using electricity, okay, to cause a chemical change. Now the other whole part of this would be a battery where we're using chemical changes to cause electricity. But right now we're saying there is a wire, and the wire is going to be connected to a battery. So one of these sides would be positive, one of these sides would be negative, and that charge difference is going to cause a chemical change in the water. And we need to understand that pretty well. Now looking more closely here, we can see that there is a red wire and there's a black wire. And red wires are typically the positive wire, and the black wire is the negative wire. So a battery is really just an electron pump. So if we have a negative side, okay, the reason this is negative is because there are lots and lots of electrons that have been pumped into this wire from the battery. And there's a positive side because the electrons have been removed from that battery, from that side. Wherever the wire connects with the solution, okay, that's called an electrode. So we're going to have a positive electrode and we're going to have a negative electrode. So this side would be positive, this side would be negative. If we have a wire that has lots and lots and lots of electrons, then when a chemical comes in contact with that, that chemical is going to gain an electron. And we know that if you gain electrons, then that is reduction. And we have a name for that. Wherever reduction occurs, that is called the cathode. And you have to be able to kind of get that sorted out. So one little mnemonic to help you remind that is you can say red cat. So reduction always occurs at the cathode. In the same way that the positive wire is positive because the electrons have been pumped away, okay, from the wire back into the battery. So the positive side, if a chemical comes in contact with that, they are going to lose electrons. And we know that when you lose electrons, that's oxidation. Now, when you lose electrons, that's oxidation, and that happens at what we call the anode. And the little mnemonic for that is anox. So you can think of red cat and anox. And that is always, always true for every different electrochemical situation, whether it's electrolysis or when we get to batteries. Both is always true. Oxidation always occurs at the anode. Reduction always occurs at the cathode. Now for us, we have to go back and say, well, what are the actual chemical reactions that occur? So a really useful chart is the standard reduction potential. Now standard reduction potential chart is a list of a lot of chemicals, and they're always reduced, which is why it's called the standard reduction potential chart. And if they're reduced, that means they're going to gain electrons. And we can see all up and down this chart that each of these chemicals here is gaining electrons. Now, not only is that happening, but it has it in order of voltage. So we can say here's the very high numbers, and here's very low numbers. So that means the chemicals at the top are the most likely to get reduced. Now, if they're most likely to get reduced, that means that they would be the best oxidizing agents. And that's not too big of a surprise. Here's chlorine. We use chlorine to bleach things, to oxidize things, to pull electrons off of other chemicals. Oxygen obviously is a very good oxidizer. That's why it's called oxygen. That's why we call it oxidation. At the same time, way down at the bottom, then we have chemicals here on the right side. So the reverse reaction is the most likely to get reduced. I'm sorry, I said it wrong. Most likely to get oxidized. So the upper left chemicals are the most likely to get reduced, and the bottom right chemicals would be the most likely to get oxidized. That means that these would be really good reducing agents. You put them with it, they will reduce other things. They'll grab electrons off of other chemicals. So they're very, very non-likely to get reduced, but they're very likely to get oxidized. But notice we have to look at this reaction in reverse. So the ones at the top, you want to look at them from left to right. The ones at the bottom, you kind of want to look at them from right to left for what they're most likely to do. Well, at the negative electrode, we've already said that the negative electrode is a place where somebody is going to gain electrons, so somebody is going to get reduced. So what do we have in our solution there? We have water. So we say, well, water getting reduced, here is the reaction for that. So at that negative electrode, we'd expect water to get reduced according to this equation. So we saw that there were some bubbles at the negative side, and the bubbles then must be bubbles of hydrogen. Now another whole piece of this is, in the solution, okay, water is not a very good conductor. So in the solution we also have to add something else to help it be a good conductor. And one thing that we added in one of our experiments here was sodium sulfate. So at the negative side we would expect the sodium ions to show up over there because they would be attracted to the negative electrode, and sulfate ions, since they're negative, would be attracted to the positive electrode. So at this negative electrode we have to really consider two different reactions. We have to consider the water, but we also have to consider the sodium. Both of those are going to happen. So we want to look at these two numbers and we say, well, which one is more likely to happen? And so the larger of the two numbers, so a negative 0.8 is larger than negative 2.7. So the one that's higher in the chart is the more likely going to happen, and that is the one that happens. So that's our reaction here, that the water is actually going to get reduced. And this also makes sense because we know that sodium actually reacts with water. So there's no way that we're going to make some solid sodium metal underwater, because it would react with the water anyway. So hydrogen gas and hydroxide ions, we would expect to see those two products at the negative electrode. Now at the positive electrode, we say that is where somebody is going to get oxidized, because the positive electrode does not have enough electrons. They've been pumped away, so they're going to pull electrons off of whatever chemical. Well, if I want to use this chart, this is the standard reduction potentials, so I have to kind of imagine everything turned around backwards. So I'm looking for reactions that are going to be oxidized. So what do I have in my solution right now? I've got some water and I've got sulfate ions. So water, water, water. Starting from the bottom, I look from the right, and this is not good. No, no, no. Here we go. No, it's got SO2s. No, no, no. Here we go. So here, way up here, is a reaction that we want to look at in the reverse direction that starts with water. So this is what water could do when it gets to the positive side. Now, the other thing with the other possibility is sulfate. So if we look closely, there is no reaction that has sulfate as a product. There's no reverse reaction that starts with sulfate. There's a sulfate over here, but that doesn't count. We're saying that sulfate could get reduced, but we want to find one where it's going in reverse direction. And the answer is, we're not going to find a reaction showing sulfate getting oxidized, because what we have here is sulfate is as oxidized as it possibly can be in sulfate. The sulfur, sulfur is as oxidized as it possibly can be. We know that oxidation number comes from the charge an atom would have if any shared electrons are assigned to the more electronegative atom. Well, as far as electronegativity, fluorine is the most electronegative atom, and oxygen is the second most electronegative atom. So if we're talking about sulfur and oxygen, oxygen is the one who's going to get all those electrons. So sulfur, which usually has 6 electrons, okay, in this case it has 0 electrons, so that gives it a +6 oxidation state. And that cannot go any higher because it only has 6 electrons. So that's the largest oxidation state it can. Remember that every atom is always the largest oxidation state is the column that it's in, the number of valence electrons it has. So this is the highest, so the sulfate cannot get oxidized. So on our chart we will never find anything with sulfate on the right hand side because sulfate cannot get oxidized. So at the positive electrode it has to be water turning into oxygen and hydrogens. So here's our situation. We've taken a little petri dish, we put in some sodium sulfate and water, and then we have added some universal indicator. And the universal indicator is good because it can tell us whether there is hydrogen ions or hydroxide ions being formed. So we said at the negative electrode we would expect to see water getting oxidized. So this situation right here, we say water getting oxidized. Let's clean this off. So at the negative electrode, which is the cathode, there's reduction, and it's water getting reduced. So we see hydrogen and hydroxide at the negative electrode. So at the negative electrode, we're seeing hydrogen gas being formed, and we're also going to have hydroxide ions being formed. And that makes sense because here we have that purple color, and the purple color is due to the hydroxide ions. And there are little bubbles, and the bubbles in here are bubbles of hydrogen gas. So at the negative side, we get hydrogen gas and hydroxide ions. Now back at our other chart, at the positive electrode, we decided in this case that water is going to be reduced, but again we're looking at this in the reverse direction. So we're going to produce oxygen gas and hydrogen ions. Oxygen gas and hydrogen ions. So at the positive electrode here, we have more bubbles, and those bubbles are oxygen gas, and we're also making hydrogen ions, which accounts for the red color. So the universal gets to show us what these little ions are doing back here. So positive electrode, we make oxygens. Negative electrode, we make hydrogens. Let's go back to our original picture. Okay, this side over here is our negative electrode. Here's our positive electrode. We said at the negative electrode we are making hydrogen gas. At the positive electrode we're making oxygen gas. And since we are starting with H2O, where there's 2 H's for every O, it's not surprising that we're going to get twice as much hydrogen here as we have oxygen gas up here. So our overall reaction would be 2 H2O's turns into 2 H's, H2's, plus an O2 gas. It's a little hard to read. And we can see that in our reaction. We can get the overall reactions for each case here from the looking at our reduction potential chart. And we can see we're making hydrogen gas, but we're also making some hydroxide ions. And we're making oxygen gas, but we're also making some hydrogen ions. And we can see that when we put in an acid-base indicator.